Hello and welcome to the SimScale webinar on mechanical and structural analysis with engineering simulation in the cloud. My name is Dr. Nagman Khan. I'm from the marketing team here at SimScale and I'll be your moderator today. I'm delighted to be joined by my learned colleague, David Short, who's a senior application engineer specializing in mechanical and structural analysis with simulation. So at SimScale, we're empowering engineers to innovate faster. What does that mean? We're here to empower every engineer to innovate faster by making high-fidelity engineering simulation accessible from everywhere and at any scale. Now, let's see why that's important for today's application. Today, we're going to see a quick workflow to simulate a nonlinear static structural analysis of a plastic push pin, like the one you can see image on the right. We're going to explore key design considerations, including survivability. So let's look at stress pinch points, deformations. We're going to look at weight and material costs and the manufacturability. This will be done using a live demonstration of the SimScale platform using this push pin project. And at the end, we're also going to show you how to set up, run, and simulate to arrive at design decisions. Now, this project is a public project which we've made available to you, so you'll be able to go in, access the project, and have a try and a play around yourself. And we'll be here to support you in doing that. Now, I'm going to hand over to my colleague, David Short, to take us through the SnapFit plastic pushpin project.
Okay, well, thank you for that. My name's David. I'm one of the application engineers here at SimScale, focusing on structural analysis. I'm going to be taking you through this technical example of a SnapFit plastic pushpin. So the product that we're going to be looking at is a plastic pushpin. Now, these type of devices, type of components, they span across many industries. So I'm sure you've seen these in your house, in furniture, but also in your car bodywork. And that's what we're going to be focusing on today, is the automotive application. And we're going to be looking at a nylon 66 pushpin, and for really assessing the structural integrity of a pushpin under operation, we need to do a fairly complex and robust finite element analysis, a structural analysis, to understand what the stresses and the forces required for the snapping operation actually are, and whether or not our design is capable to achieve what we want it to achieve and meet the requirements. So the process that we follow for our structural analysis is obviously starting from the geometry. We've got our three-dimensional CAD model, and to explain a little bit about the problem that we'll solve as well, we're going to be looking at a 10mm insertion and extraction operation. So one cycle of this pushpin's operation, and we want to be then understanding the mechanical behavior of the device. So we've got our three-dimensional CAD model. And then what we need to do is get that ready for simulation. So are there any ways we can optimize that and have a more efficient simulation? So the first thing I've done is created a quarter symmetry model. So we can then reduce the amount of work that the solver has to do. We can cut this thing into a quarter and make the most of the fact that we've got some symmetry planes here, so we can simplify our simulation just a touch. We're using automatic meshing to create our finite element model, and we're going to be using highly accurate second order finite elements for actually capturing the material and geometric behavior during the simulation. The physics that we'll bring into the picture, it's going to be the big three. So all types of nonlinearity we're going to have in this simulation. So firstly, a nonlinear contact between the punch hole and the push pin. We're going to be looking at large displacements, obviously, because we have to push this push pin all the way through and back out of the punch hole. And we're going to be applying nonlinear material properties. So we're using an elastoplastic material model here for the nylon 66, and you can see the stress strain curve that we will then load into the material definition on the SimScale platform, such that then the response will coincide with the uniaxial test data that we actually supply to the simulation. When it comes to solving the simulation, we'll be using the default solver straight out of the box with a nonlinear static analysis. And obviously, being SimScale, it's all cloud driven. So obviously the advantages of multiple parallel computation come along with that. And I'll show how we can think about making the most of that once we get into the platform a little bit later. So in terms of the results of interest, the design insights that we actually get out of a full resolution structural analysis like this, we start with looking at the shape, the deformation that this pushpin actually goes through after a single insertion extraction operation. So we start with our undeformed shape on the left over to our final deformed shape. And we can see, so after one operation, we have quite a lot of permanent deformation caused by the actual insertion and extraction operation. And we can also see the stresses that have developed during the operation. So we find peak stresses at the point where the thickest part of the pushpin goes through the punch hole, and we see those peak stresses. And it's really important to then understand, are those peak stresses going above our ultimate strength, in which case we would be expecting to see failure of the model of the material in reality. And so if we have large areas where we go above the ultimate strength, then we really need to start considering design alterations, design changes to try and minimize and reduce those kind of areas, particularly if we're looking at a pushpin that needs to survive multiple operations. You get some pushpins that are designed just to survive one, and then on the second one they're going to break already. And but some need to be run 10 times, for example. They need to have a longer longevity and durability during their lifetime operation. So depending on the requirements of your product, then you can use the results differently from the simulations. So we've looked at deformed shape, we've looked at the stresses both during the simulation and those stresses that are left over after the operation. So those are the residual stresses caused by that permanent plastic deformation. And then we've extracted, so during the simulation, the forces required to cause the insertion extraction operation. So that's what we're looking at. And this force history on the bottom right, you can actually see the force required to insert and then extract the pushpin. And we actually see quite considerable amounts of spring effects as well as we jump through. Then it'll spring through the punch hole once we get past that thickest section, and the same will happen in reverse on the way back as well. All right, well, now is the time to actually get into the platform, see it in action, see what it looks like, and so you can get an understanding of SimScale and the approach that we would take to this type of simulation. Okay, so here we are in the SimScale platform. We're looking at the three-dimensional results, first of all, to understand a little more sort of qualitatively about the deformation, the behavior, so that we can get an initial impression of what's really going on. We can pause that and we can slide it through to understand where are my areas of highest concern. Now, I've capped the legend here with the ultimate strength, so we can see that anything that is completely red are areas of stress that go above the maximum strength of the pushpin. So we can see considerable regions of yielding or of stresses going above that maximum strength. So we would really need to be starting to consider design alterations to reduce the amount of chance of failure essentially within this product. So that is where something like SimScale would really come into play. We can run multiple design iterations. We can look at as many different design variations as we like, have multiple geometry in our project, and test those different designs to understand which one will be optimum, which one meets the requirements, and so on and so forth. So that is really the value of SimScale and bringing simulation within the design cycle, so you can actually quickly understand if these failures are going to be expected, and then you can remove the risk of them without the need for lots of physical prototyping. So if I just go back to my solution fields there, we can have a look at some additional result outputs. So if I pause it here, I'm actually very interested in where are my areas of not only peak stresses going above the ultimate strength of the material, but I also want to know where do I have regions of permanent deformation. So if I turn on my ISO volume here, what I've got here is an equivalent plastic strain, and that is going to be showing us the areas where we're going to be seeing permanent deformation. So we can see that as well. If we go right to the end of the simulation, and we can see where do we have those regions of absolute permanent deformation left over in the structure. Okay, so we've looked at our displacement or deformation behavior using the animation. We've looked at our maximum von Mises stresses, and we've also identified regions of permanent deformation. Now, these are all critical result quantities that are going to be really valuable for those design engineers looking to optimize the products for real life usage. Let's have a little look at the simulation output, how long it took, and what we've actually done to set up a simulation like this. So here's my simulation run. You can see that it took 109 minutes to run the nonlinear analysis, and within this run, what you get out of it are those 3D results that we've already seen, but you also get graphical output for the reaction forces, for example, on my plastic pushpin. Now we can see the time history, or the force history of the force required to complete the insertion extraction operation on the pushpin. So where did this simulation start? Whenever we bring a geometry into the simulation, then we hit the simulation library, where we can see the full range of interdisciplinary simulation types that SimScale offers within our analysis ecosystem. So I've used a static analysis, and I've added complexity step by step to include the nonlinear static behaviors as well. So we're running this as a pseudo-static analysis using nonlinear. So we're using a nonlinear static analysis which uses load increments to step through the problem to finally converge on that final answer once we've gone through all the load increments or pseudo time steps through our nonlinear analysis. So we're using a nonlinear static. We're then applying a nonlinear contact between the pushpin and the punch hole surfaces. We're then applying nonlinear material properties to our nylon pushpin, and we're modeling that as elastoplastic. So that's done by uploading a CSV of a true strain, true stress curve in table form, and that is applied then directly to the material behavior. So we can then bring that into the actual structural analysis itself. So we've got a nonlinear contact, we've got nonlinear materials, and then the nonlinear geometry and large deformations and large displacements are going to be taken care of by default by the solver itself. In terms of constraining the model and setting the enforced displacement, I'm fixing the panel with a number of both symmetry planes and fixed values on the punch hole structure. So we've got our fixed bottom and symmetry planes, which lead to a nice, robust and constrained situation. The enforced displacement is enforced in the Z direction on the top of the push pin itself using a table definition. So we within our simulation is going to be running for 1 second of pseudo time, and at half a second we're then at the full insertion, so 10 millimeters insertion, and then we put it back out to 0 at the end of our simulation. So we're doing 2 steps to our simulation: insertion and extraction in a single simulation. Okay, and that's really all there is to it. We've got our boundary conditions, we've set the nonlinear physics for our problem, and then we're using SimScale smart defaults for the solver settings and simulation control, and then we just need to be using and be thinking about the mesh that we actually want to use. I've used a purely automatic mesh with fineness set to 8, and I've applied second order elements to the structure, which is going to be crucial for actually capturing the accurate deformation behavior, and thus the accurate strain and stress behaviors as well within our structure. So when we've got some fairly thin members like this, we want to make sure we have second order elements to capture the bending appropriately and to capture those deformations realistically during our simulation. So that's using our automatic mesher and second order elements to get this simulation off the ground and running. So that's all there was to it: a complex nonlinear static analysis with SimScale's default settings, and also a nice amount of design insight gained after an hour, after 109 minutes of runtime. So that's all I wanted to show on the platform itself. Now, obviously, questions I hope are going to be coming in, and we can jump back onto the platform as well to answer those platforms if needs be. So that is what I wanted to show. I'm going to switch quickly back to the presentation before handing back over.
David, thank you so much. Fantastic demonstration. Should we take a few questions now?
Sounds like a good idea. Yep.
Fantastic. Let me put up the questions. We've got about 4 questions so far that have coming in. First one is the permanent deformation a desired feature of this optimized fastener, or is it more of a result of a compromise between various other considerations like cost and etc.?
Yeah, very good question. So a lot of these fasteners, it'll be sort of it'll be part of the design that they can withstand some levels of plastic deformation, but in this case, I would really say that was far too much stress over and beyond the ultimate strength in large regions as well. So that's a big red flag saying this is likely going to fail on the first insert extract type operation. Yes, this can be built into designs as well when required, but you wouldn't want it to break on the first go. Normally, it will be built in such that it could withstand 2 or 3, and then break, and that allows you to make kind of cheaper products and things like this. But yeah, so the plastic deformation is a result of this design that we've run, and it's not the best design, it would turn out. So where I would take this next is add some design alterations. So maybe add some fillets up at the connection between the head and the actual wing, and then that would allow for a little less stress concentration up there, a little less plastic deformation, and then we take it through another design iteration to see how that performs on a second run.
Yep, fantastic. We've got more questions coming in, David. Next question is there a way to create dynamic forces on the pin?
Can you repeat that one, please?
So the question is from Ankit, and it's, is there a way to create dynamic forces on the pin?
Yes, absolutely. So if you wanted to run this rather than a pseudo-static analysis, you could set this up as a full-on dynamic analysis. If you wanted to see maybe on a fast insertion, what are the dynamic relations that are actually excited during a fast insertion. So I would recommend first doing your frequency analysis, finding your eigenmodes, and then moving into a dynamic shock type analysis where we could quickly run it through and then measure the dynamic response in terms of a time history, then do a Fourier transform on that and work out which eigenmodes have actually been excited during this dynamic time history, and take it from there. I haven't seen it often, to be honest. I haven't seen much dynamic applications in this field, but certainly we have the capabilities to look into it.
Fantastic. And get in touch with us, Ankit, if you have a particular project in mind. We'll be able to discuss it with you one-to-one as well. Thanks, David. Next question is, there's a few questions coming in, David, so let's try and get through these. Next question from Stephen is it possible to show full symmetry results?
In the SimScale post-processor, not currently, unfortunately. It's on its way. So when we make these symmetry planes, we also want to then reflect those results across symmetry planes, but it's not in our new post-processor yet, but it is on the list of things that we want to have in the platform. So hopefully it won't be long to wait for that kind of feature.
Great, thank you. And another question is, how do you determine the pseudo time configuration? I'm not 100% sure what Michael means. Perhaps you can shed some light on it.
Yeah, it's a good point. So what I understand from that question is how the question is, how have I come up with the load increment steps? How did I know that they were sufficient? The real answer is that can be optimized. So I've just done a pretty basic, I'm going to do this amount of load increments and I've split it up equally. Actually, if you want to get the absolute peak stresses and things like this, you should actually cluster the increments around the point of maximum stress. So when we saw it went sort of a quarter way through the simulation, we're seeing that peak stress where it's on its full deformation. It would actually be more accurate to add smaller time increments around there, so we actually resolve the physics with a little bit more resolution. But this is an arbitrary choice. So for me, those initial design iterations, I'm just going to use a fairly standard approach with constant load increments. But as we move further into validation and quality assurance type exercises, then we would start looking at that kind of physics resolution.
Thank you, David. Okay, we have a question here. This is interesting. Why is a static analysis done here? Because the forces are changing rapidly due to contacts. Would a dynamic analysis be required?
I would say that the forces are not changing quick enough for a dynamic analysis. So in a dynamic analysis, we would be expecting inertial effects to come into play, and for me that's over sort of 10 meters per second in terms of an impact velocity. But below that, if we're not thinking in G's and actual dynamic shocks, then I don't think this is sufficient for coming into the dynamic domain, in my opinion.
Okay, fantastic. Another question from an attendee is, when is it better to choose smaller elements instead of a second order ones?
So you could do both, to be honest. But second order elements are much more efficient because they can resolve in the displacement, in the deformation, a quadratic function with a single element. And if you think about a first order element where the shape functions are just linear, you're going to need at least sort of 5 elements to have some kind of good representation of a parabola or quadratic sort of displacement relationship. So if you go with first order elements, you're going to need lots and lots of very small elements to get the same results as you would get with a fairly coarse second order mesh. So I recommend always, when possible, use second order. It's going to be more efficient and more accurate. But there are the cases where we actually want to use first order to streamline convergence and things like this. But there we have to just be mindful of the fact that we're going to be approximating curvature rather than really having it explicitly in the shape functions.
David, thank you. Let's take a couple of quick questions. I'll post these together to you, David. So the first one is, can we input frictional effects at the contact? And the second question is, what support do you offer to SimScale customers in setting up a simulation like this?
Of course. Okay, so with the first one, frictional contacts, that's going to be part of the nonlinear contact definition, and that can be brought into exactly a simulation just like this. You can simply add friction onto the nonlinear contact with a Coulomb coefficient of friction. That's going to be a static coefficient of friction, and you add that in at the contact itself. But you've got to bear in mind that's an additional layer of complexity. It's going to be harder to converge, potentially longer runtime, and in the majority of cases, friction doesn't play a massive role in a lot of these type of analyses. But we have it there, and you're able to then test that out. Now, on the support side, of course, we're there to help. So for our professional users, we've got 10-minute response time on our in-platform chat. So really, with myself, the rest of the engineering team, we're there to jump into your projects if you need help, and set it up from the ground up. And I mean, when you sign a subscription with SimScale, there's onboarding processes, training involved to help you get started, and we really do a bit of hand holding on those first simulations to get you up to speed, and so that we can make sure that you're really seeing value out of SimScale results in the shortest time possible.
Absolutely, and that support is absolutely critical for engineers working on on live projects, especially when they have deadlines and they need to get through multiple design iterations. Thank you, David. A quick follow-on question actually from that has come through. Does SimScale suggest design alterations for improvements?
That will be left in the hands of the designer. So when we see larger areas of stress concentration, it's going to need a little bit of design engineering expertise to say, that's the area where I need to apply a fillet. How could we change the kinematics behavior using either adding mass or taking mass away, so weight reduction, which is also obviously a design consideration as well for these types of products. But that's really left in the hands of the designer. We're there to give you the results, and then that's going to have to be on your design expertise, saying how can we then reduce stress concentrations by adding fillets, for example, allowing smoothing out of those stress lines throughout the model.
Fantastic. And if you have any more questions, you can get in touch with David Short on dshort@simscale.com. David, thanks so much for answering those questions. Let's take a quick look about how someone can get started now with SimScale. And I'm just going to, can you see my screen? Okay, sorry about that. So time to roll up your sleeves. So if you found this interesting, which I hope you have, you can get started easily with the simulations shown in this demonstration. So we will send a link and a copy of the video to everyone who registered for this event. So this plastic pushbin project is live. It's public for you to take a look at as well. And you can also request a one-to-one demo by just contacting sales@simscale.com. One of our senior application engineers, such as David, will be there to help you show a full demonstration of the SimScale platform and discuss one-to-one your projects and how we can help you as well. I hope you found that interesting. David, any final comments from your side?
No, that's all from me. Just a big thank you to all of those attendees that have taken the time out to watch us.
Likewise, from myself as well and everyone at SimScale, I hope you enjoyed that. And we'll be in touch with some follow-up resources so you can all get started with simulations in SimScale. Thank you.